Hello, am I audible? I couldn't hear any one of you.
Yes, audible.
Okay, okay.
Yes, sir,
Thanks.
you are audible.
Okay. Okay, let us start. People have joined. So before that, I'll just share this link for the last time. Thank the NPTEL has given me another opportunity to help you people. So this was not in the plan. So this is out of the schedule that I'm doing for your exam purposes. So maybe this will help you to write your exam on 25th. So first of all, I'd like to wish you all the best for the exam and do well. I hope this helps today. So we'll be covering most of the things that we had done all throughout these 8 sessions that we conducted. And I'll also give you some more insights that we couldn't cover and the course didn't cover. Didn't have the scope to cover. Since we have some time, we'll take 5 to 10 minutes to uh, 5 to 10 minutes to go through some of the machine learning practices that you can incorporate in your projects, and then we will go to some questions that like modeling the or um, modeling the type of questions that may be asked for your question for your exam. So that's the plan for today. Oh, I share? Okay, I shared this link, and let me share the YouTube link as well. And this is the link, so you can view the videos once in your leisure. So let's start. So today let's start with some practices in machine learning that you need to perform. So I thought about covering these 4 topics. I'll just brief you on these, and these are not anything to do with maths or something, but these are helpful when you're training models. So till now we have seen a lot of, so number 1, we have seen a lot of models, and we have seen both supervised models and unsupervised models. Let's consider a supervised model. For a supervised model, say one is doing classification and the other is doing regression. So what are the type of matrix that you can use to quantify how well your model is doing in each of these cases? So can anyone tell me what are the matrix that you can use? In classification, you can have a lot of matrix. Can you give me a couple of them? So for classification tasks, you first of all have the loss that you maximize over, the cross entropy loss. We have seen this in the logistic regression session as well. This you can see the loss that decreases. This is the epoch, or the number of iterations to the training set. Number 2 that everyone uses is accuracy. I'm quite confused why people are not responding. Make it an interactive session, to be good for you. So accuracy, precision, and recall. F1 score, so on. You have many scores for classification tasks, since this is a discrete set of variables that you output, say 1, 2, 3, 4, to say the class where a particular sample belongs to. In regression, popularly you just plot the loss. This is the loss or the mean square error, or the mean absolute error, whatever MSE, ME. Yeah, go ahead.
Mean square error, mean error.
Yeah, Professor Sandeep.
Yes, root mean square error भी है ना सर वहाँ पे? by the
Yeah, root mean square error or mean square error, they'll be the same thing. Actually, the j theta that I'll come to that. So mean square error is what? It's just 1 by 2m, the difference between the predicted minus the actual examples. That's it. Root, if you take, this is the root mean square error. Is that okay? Any question? Somebody has a question. So this is a mean square error is the amount of deviation from the y equal to say f of x line that you're trying to plot, or w equal to y equal to mx plus c line. So what is the deviation that each point has from this line? So this is the, not this distance, but this distance. The amount, the difference in the y and the actual level of y. So this is the mean square error. These are certain things. So keeping these things in mind, we can know what is the practice. So these are for how do we report how well a model is doing. So what is our objective? Can anyone tell me, why do we build a model? We build a model to
relationship between the input and output.
That is okay, but why? What do you want to build a model just to build relationship between the training sets input and output?
To find the target value.
To find the target value on unseen data, you need to specify the unseen data. Yeah. So think of a system that you have in your phone that would recognize your faces. These would see your faces as unseen data to it. Although these things record your face and so on, but ideally they should be unseen data, and so they should also know how to work on these unseen data. Maybe for a cancer classification task. So you can make a model on the training data, and then you get a new sample. You will try to put that sample in and get the output, whether it's a positive or a negative sample. So build a model for an unseen data, for a real world applications. Maybe we'll write world application where all the data is unseen. What do I mean by unseen? Not used by
training purpose.
Yeah, in the training set. So, but for this we need to have evaluation matrix to tell how your model is doing before deployment. So for that we have something called as, so if this is the training set, you often break this up into say 3 sets. You train this on this set, you have another set, I'll come to that, and you have the test set. Yeah, that's correct. Train test, cross validation test, and the set and the test set. So I'll just, this 2 sets are used for your training, used directly or indirectly. I'll come to why indirectly in training. And this is the set on which you report your results on, which is nothing but the generalizability of the model, or the generalization capacity of the model. Now, what are the practices that you need to do? There are people, what they do is, so consider learning rate, okay? Consider learning rate, and then you consider things like batch size. I'll come to what is batch size and other things. Say L2 regularization coefficient, model architecture, etc., etc. All these things that you cannot optimize directly using neural network or back propagation. Cross validation set, or this is the cross validation set.
Sir, can you repeat your voice?
Yeah, okay, yeah, sure. What I said is, I'll come to it again. So what do I mean is, when you're training a model, okay, you train, and then you train a model, you learn the weights, right? You learn weights by gradient descent. But there are something called as the hyperparameters that you cannot learn by gradient descent. That is considered the learning rate, that you update W as W minus alpha, or let us write LR only, LR into DL dW, right? So this learning rate is a hyperparameter. So you may select 0.1, 0.001 and so on, and evaluate your algorithm on all of these, and then evaluate the metric, evaluate a metric on the CV set. Remember, never evaluate, never select hyperparameters using the test set, because in that case you're specializing your hyperparameters to work on the test set. Your test set should be ideally unused, totally used, or yeah, I'll do question revision of question assignment 4, and whoever's like Ritu Rishparna, you can go and see the video that I had discussed there on week 4. The mathematics has been very clear. I did it very clearly. I'll also do questions from that week today, Bayes rule and all. So for week 4, it was purely mathematical. So probability models and all I have covered in details in the tutorial of 4th week. You can go ahead and watch that also. That will, I think, help you more than today's session. I'll cover questions regarding that, no problem. Evaluate metric on the cross validation set. Never use the trends, never use the test set. So whatever you want to find out, say you want to find out the learning rate, you will evaluate, do the same process on the cross validation set and see, evaluate your model on the cross validation and see how well your model is doing. And finally what you will do is, you will when everything has been selected, say the model architecture, L2 regularization, batch and all, you will go and report your results on the test set. Is this thing clear? I hope it is clear. This is nothing too complicated. So this thing we covered. So there's another thing called a k-fold cross validation. So what do I mean by k-fold cross validation? I'll just write it over here. So you divide your data set into k folds, say 1, 2, ... k. You keep one, or rather you can keep two, one as test and one as there. Say you keep two, use this as cross validation, use this as test, train on this, and use the cross validation and do the testing respectively, and you iterate. You select these two for all combinations. Say you select the test set first, j equal to k minus 1, and do k epochs, k iterations. And these are independent, ideally independent sets, and then report the average accuracy. So in papers and all, you'll see 3-fold cross validation, 5-fold cross validation, and so on. So is this k-fold cross validation clear? So you divide the thing into chunks, keep one as the test set, and use the rest for train and cross validation. Is that okay?
What are the best use cases for train test split and k-fold cross validation?
That is just a heuristic. People used to use a 80-20 split. 80, maybe 70, 10, 20.
No, I'm not asking the proportion. I'm asking the best use cases. In which application the train test split is best suited, and in which application the k-fold validation is best suited.
Okay, this depends upon when you have a very large data set. Ideally, then you don't need a k-fold cross validation. But in a smaller data set, ideally best it's k-fold cross validation. Because in that case, the extreme cases, leave one out and train on the rest. So medical images and all, people in neuroscience would leave all the one example out and train the model on all other examples. So when you don't have, say you have 20 samples, that time you can't do sort of this thing. So you train on 19, keep one out. Okay, is that okay?
For big data, the train test split is good.
Yeah, you can just keep a fixed test split and a cross validation split, because if the data size is too large, you don't need to do k-fold cross validation. If it's smaller data size, you do a k-fold cross validation. Ideally, why you're doing this? Because one sample can be a noisy estimate of the loss that our model can have, If you have it 5 times, so your by law of large numbers reduction of variances, you will have a reduced variance or something like that. But ideally, if you select it randomly, that any random sampling of the data set would actually give you near the mean itself of the 5 cross validations. Is that okay?
Okay, got it.
Yeah, in some cases, papers and all, people will ask for k-fold cross validation when the data set is small, but for ImageNet and all, you don't need such things. So large data sets, you generally don't need. So now I'll just do the last before going to learning curves, which is a bit theoretical, because people had a lot of doubt in bias variance trade-off. So I'll just talk about that for a couple of minutes. Before that, I'll just say what do you mean by, just a second, number of parameters decrease with regularization, what to increase the number of parameters. Okay, this I'll cover with in this only. Okay, and the last thing is just for your understanding, so there are many ways to some learning algorithms. So these are learning algorithms or the optimization algorithms. So you can use a normal gradient descent, which means do the gradient descent on entire data set. You can use a SGD or a stochastic gradient descent. What is the idea? Can anyone tell me? So stochastic gradient descent will be taking a random sample and doing a test. So you have this test, you have this example, you use one of this sample. Yeah, go ahead.
Batch sampling, no?
Yeah. You just take an example and update. So the learning rate can be a bit noisy, but generally it will converge this way. In gradient descent, you never have a random noisy learning curve. You always, the loss will decrease because there is no randomness in the sampling. So when you're sampling randomly, you're not learning everything in one epoch. So these are for every epoch, and here it is for one iteration. So one iteration is one example and you're updating, and between is something called as a mini batch gradient descent. So where you take m examples and update. So if you do some coding languages like TensorFlow, Keras, PyTorch, they'll give you batch size. So you select batch size of 128, 64 and so on. So you take 64 samples at a time and update your learning curve. That actually helps you reduce the variance, but anyways you have this is mini batch. This reduces the variance and this is SGD. So if you have a doubt regarding these things, you can ask. So instead of calculating the variance on this entire data set, on the capital M, you take a subset of the data and do stochastic gradient descent or a mini batch gradient descent. That's all. So you update after, when this is helpful when the memory is very small. So this is, why do you need this? Say think of a data set which is hundreds of GBs. So you cannot read all the weights at a time and calculate this loss and then backpropagate. The RAM cannot store all these things. The memory cannot store it. So what you need to do is select smaller batches, read them and update your equation ad hoc. So you do it separately, and I kept on iterating the thing about epochs, and epoch is the number of passes to the training set. So that's more or less about it, about learning algorithms. These are, if you have to take an optimization course, you'll be doing these in details. But anyways, you use this to train your learning, your classifiers. But these three learning rates are learning algorithms are very important. Basically, people use it all the time. So I'll come to learning curves now, and then we will go to revision that I have planned for today. So learning curves. So what do I mean by learning curves? So
Minor, where the gradient descent is applicable mainly.
Gradient
Just like you.
So
we
spoke about gradient descent, right? So we take the derivative and update w by w minus alpha dw by dl by dw. You update the weights.
Application I'm talking about.
You learn, you use it to learn neural networks. You learn any parameters like linear regression, logistic regression, and all.
Okay, got it.
So you backpropagate the loss and tweak your weights so that it's the optimal point. So I showed this cartoon many times. So you sort of decrease your W's to get to the
Yes.
optimal point.
Yes, cost function.
Yeah, so based on the cost function, you actually change, you see the gradient, the amount of gradient you have a particular point, and continuously decrease that. So learning curves would be, the ideal learning curves is you increase the training set size. And you have something like a loss. So there is one thing known as the training loss. So this is the training loss. So why am I drawing it this way? You see, for a single sample, a model will typically learn everything, right? There will be just a delta t, right? You'll know that, memorize that point perfectly. But this is not a loss, this is error percentage. So 0% error you will have, because you will exactly know which point that is. And when you increase the number of samples, what happens is error increases. That's what I've drawn here. And ideally, if you have a good system with low variance and low bias, so you will not have this shooting up. So this is a very low bias system where increase in the learning curve is shooting up. The low bias. This is medium bias. So how do you know that your model is overfitting or underfitting? That's the question. So so I'll use the same color for the training set, and this is your cross validation set. What do I mean by error percentage on the cross validation set? And this is the size of the training set. So how do you interpret this curve? So this is, say, 70%. So this is 0. So you interpret this curve as, you start off with a particular error, right? You are training on one sample here. So ideally you give a lot of sample to the cross validation set. What will happen? You will have a large error, right? Your model is not trained to see many samples. If you just see one point on this entire space such that it is distributed this way, you want to fit a linear regression, and you just see one point, what will it do? It will fit a line like this, or so, in many ways. So what will happen? The loss will be typically very high for the cross validation set, right? The error will be very high. But for the training set, the error will be very low, because it will learn this point. The MST will be 0, accuracy will be 0, and so on. Is the idea clear? This is very important, that you need to plot while you're doing your programming and stuff like that, to understand in which direction you'll go. So when this distance is large at convergence, what do I mean? What does this imply? That
High variance.
Correct. So what is actually happening is, it is not generalizing. Very good. So at the end of the day, your model is learning very well on the training set. Error is very small, but the cross validation error is very, very high. So in that case, not generalizing, it's high variance model, and also low bias model. So we have seen that these two terms are almost inversely proportional to one another. So we would like something like a medium variance and medium bias in this sense. What do I mean by this? Something like this. So where the training accuracy and the cross validation accuracy asymptotes, CV and train asymptotes with increasing number of training examples.
Literal meaning of asymptote?
Asymptote means you are tracing one line, going towards one line. You will never touch that line. So for example, y1 by x will never touch x, but it will go near 0. That's this.
Right, approximate.
Yeah. So y is equal to 0 is the asymptote for 1 by x. So for curve 1, what will you do? What are the hacks that you can employ? What can you do? So for this, you can try regularization. regression, more training data. And you can also hope that the more training data finally will convert, sort of a thing. And training on more data is automatic regularization, because you're trying to fit on more data. You can clearly see, so your model will not, this line will not deviate much if you add 1 point. So this is a side note, that adding data is also regularization only. So and use a simpler model with higher bias. So in the second case, it can be divided into 2 parts, where both train and CV accuracy is low, error is low, to be exact. So you are done. Or both are high. This means your model is underfitting. So in this case, use a more complex model. So this is the sort of the medicine for machine learning. You need to know when the model is overfitting and underfitting, and accordingly increase your variance, increase your bias, or decrease your bias. So in case if your model is underfitting, you need a more complicated model, because it's not being able to model this. And similarly, if you are overfitting, you need to add regularization or something like that. So that was regarding these learning curves, how to increase the number of parameters, decrease bias variance trade-off practices. I've covered all of these. These are some of the practices that you do in machine learning. And if you have any doubt regarding this, so this is the first part of today's session is over. So we'll go to the revision questions that will help you sort of solve the questions, as many of you suggested to solve. So if you don't have any doubt, so let's go to the questions that I have sort of put together for you today. So let's do this simple question. Once we had done this, but I'll just reiterate this. So this is a very likely question that you can be asked. So you want to calculate this is known as the contingency table. You will be told to build the contingency table and find out precision, recall, and stuff like that. So what does it say? I have 1000 mammograms. Say 50 of them have breast cancer. Our model flags 100 of them as positive. So I have put actual labeling along the rows and the predicted labelings along the column. So you can see this is the sample contingency table where you predict to be correct. If your predict is correct and it's actually correct, is known as a true positive, where I've covered this once. So actually it's positive, you say negative, it's a false negative, and so on. So true and false is signifying whether your thing is correct, your prediction is correct, and this positive or negative says that you're either saying a positive or a negative. So 2 cross 2, you're filling up this contingency table of 4. So positive means you're telling a positive class, negative means that you're filling a negative class. So you can either be correct in saying a positive class or wrong, that is in case of a false positive or a false negative. Correct. Go ahead, you have a question. Okay, no questions. So
No questions, thank you.
okay, so the thing is, so you have, say the question is, you have 1000 mammograms, so the total is 1000. I'll just write it over here. So how do I fill this table to calculate? So it says 50 of them have breast cancer. So this is true. True examples are 50. Our model flags 100 images as positive. So our model says this sum is 100. Is that okay? So model predicts 100 images to be positive, out of which 20 have cancer. So where do I put 20? Can anyone tell me? Immediately I can put 20 somewhere.
In the first one.
Correct. So I can put 20 here, because it says that 20 of them have cancer out of 50, which
True positive.
yes, so it's a true positive case. So what will be the amount of false positive that it is saying?
30.
30.
Very good. So that's simple for me. So, it 30. No. Our model flags it's 80, right? So our model flags 100 of the images as positive, right? So 100 images are positive. Out of that, 20 images I'm correct. So how many images?
80 then negatives. False
Yeah.
false.
False positive is 80. So 30 is what? So you have 50 examples that were actually breast cancer. That is your false negative, right?
Negative, no?
Yeah.
Yes.
So you had doubt in here. So you had sort of mixed it up. So anyways, so there are 50 examples, out of which 20 are correct. So 30 are wrong. So 30 will be this. So 50 positive, original positive. So this along the row it will sum to 50, and along the columns it will sum to 100, because your model is saying 100 of them is sort of having cancer. So this you can fill up. What is this number?
The 870.
Yeah, 870.
70.
So this saying this to be 870. So what is the accuracy that you will get for the model? So this
890 upon 1000.
correct, or 89%. So you take this true positive and true negative and divide by all the examples. What is the precision? Precision is the number of times you are telling example is positive that is actually turning out to be positive. So it's true positive plus by true positive by false positive. Just remember this anecdote. So you threw a dart on the dartboard. How many times are you hitting the same particular spot? So that is your precision. So if you may not hit the perfect spot, but you're hitting a particular spot, how many times how close are you to that particular spot? So that is known as precision. So in this case, what will precision mean is every time you say correct, so how many of those are actually in that particular position in the dartboard? Is that intuition clear? So every time you say correct, so it will be always out of that, say how confident you are. So true positive here in this case is 20. And how many positives have you told?
100.
100.
Correct. So it's 0.2. So you see your precision is poor. You should have sort of a larger precision ideally. So this is a measure of how confident you are. So in case of this cancer detection and stuff like that, you should not make people worried. Just like by saying that you have cancer and it eventually turns out to be a false positive. So you should not do that ideally. You also should not do something like that if somebody has cancer and you say don't have cancer. That is also very dangerous. That is more dangerous actually. So that is known as recall. So recall means out of the total examples that were positive, how many did you report to be positive? So in this case, what is the meaning? So you have 20 you reported and total number of examples you had to be positive was 50, right?
50.
Correct. So 20 by 50 is 0.4. So sort of these are two different numbers, giving you the intuitions that I said just now. So the idea is how do I club these two? So that is known as the F1 score. You sort of take a hyperbolic mean of these. So 2 into 0.2 into 0.8 by 0.4 by 0.2 plus 0.4. That is equal to 0.8, 0.16 by 0.6. This is your 16 by 60. So you divide by 4 by 50. So this is your recall, is your F1 score. So this is all about evaluation of matrix that we covered in week 1, and bias variance data. All these things were covered in week 1. So we'll go to week 2 as well as week 6. Sort of try and go ahead.
Mine F1 score. Could you please repeat? F1 score
is just the product of the precision and recall by the sum of precision and recall. So the maximum F1 score is also 1. So when P and R is equal to 1. So now this was week 1. We revised. So now I'll go and revise week 2 and week 6 for you. That will be through this example. So this was one of the last year's assignment questions. So we'll be doing this sort of to help you understand the type of questions you may be asked. So you have, say, these data points. So you have some x, 6, you have 7, 5, you have 4, 10, you have 4, this is 5, this is 6, this is 10, you have 9, and 3, you have 4. So you want to sort of fit a linear regression. You could do anything, but let us fit a linear regression. So in week 2 and week 6, we did the linear regression and this neural networks, MLPs. In those cases, it is this back propagation and so on. So first of all, you need to calculate the loss that I was talking about, the mean square loss. So say at a particular point, your theta is 2, 1. So what is the loss at that particular instant? At theta equal to 2, 1. So let's do it. So I'll put theta 0. So what is the mean square error? Just to recall, 1 to m y hat minus y, right? Square by the total number of examples. Is that okay?
Yes, sir.
So y hat is the parameter of theta. So parameter of theta, here you have represented y hat as two parameters, y theta 0 and theta 1. So that is nothing but, I'll just replace as y hat over here. So let's calculate this now. So it's 1 by 2 into 4, you have 4 examples. Then you have 2 plus 6 minus 7 square plus, if anywhere you have a doubt, you stop me.
Are we calculating mean absolute error?
Yeah, mean square absolute error, MSE loss.
Mean square, okay.
Mean square error. Mean absolute does not make any sense. Mean square is always a positive number.
Okay.
So you see I'm just putting value of x here, y here. So this is the value of y hat that I'm predicting, and this is y. So y is equal to mx sort of a line plus c. This is a y equal to mx plus c line, right? You can clearly see. This is a line equation. M is defined by theta 1, c is defined as theta 2. So is that okay? You get the geometric interpretation. So linear regression will always fit a line or a hyperplane in case of a multi-dimensional case. So in the next example, yeah, you have a question?
No.
So what will be the next term in this? Somebody?
Sir, I have a question.
Go ahead.
So what is the value of theta 0? I just missed it.
Oh yeah, I have said theta 0 is 2, theta 1 is
okay.
1. I have said this is 1. This is
okay.
1. At a particular instant, I'm telling this is that particular t you're optimizing. This may not be the optimal point. So, but this is at a particular point you're told to calculate the loss.
Okay, so generally in the numericals, when it will be asked, the value of theta 0 and theta 1 will be given.
Ideally,
right?
it should be given, yeah.
Yes. Or we can assume.
Or you can sort of be told to find theta 0 and theta 1, but there'll be a sort of easy equations that you can solve using a differential and set a differential.
Okay. So
that I'll show you just now how to do it.
Okay. Thank you, sir.
Yeah. So 2, 6, 7. Can anyone just prompt the second term?
2 plus 5 minus 4.
Correct. Someone else with the third term?
2 plus 10 minus 9.
Correct. So you have understood. And the last term is 2 plus 3 minus 4. I'll not do the calculations. You can, or let's do it. So this is sort of just for the sake of completeness. 1 by 8. This is 1 minus 1. So 1 plus, this is 2, 3, 9 plus 1, 3, 9 plus 1. So it's 20 by 8. That is nothing but is equal to 2.5. So this is the loss function. So at a particular value of theta. So now for gradient descent that we did in week 6, what will we do? We will calculate the derivatives, right? And
yes, sir.
And we will update theta 1 as theta 1 minus alpha dj d theta 1 and so on. So let's do that as well. Let's calculate
J theta is the loss or cost function?
Both are the same thing, right? So it's the same name given to the same thing. Loss is the name of the cost function. Cost function is another name, synonym for loss. The function you optimize is known as the cost function, and the loss is the value of the function that it takes at a particular point.
Okay.
You can look at it this way. This is nothing, no rocket science here, just terminology. So let's do the derivative. Let's keep this point in mind. So let's go down and this. So since Richa was asking, so this type of questions may be asked where you may be told to find the optimal theta 0 and theta 1. In that case, you can just take the derivative and set it to 0. So in our case, let us take the example of j theta is equal to 1 by 2m, and I have in my lesson also given you the closed form solution for this. So you can go back and look at the week 1 if you want, if you have time after the exam maybe. Ideally, you don't need this closed form solutions for the exam, but still, if you're interested, you can go back and look at them. So it's theta 1, theta 0 plus theta 1 x minus y square, right? This is the equation that we were sort of finding the derivative for. So somebody just go ahead with helping me to find out dj theta dj. You're told to find out the gradient of j. Gradient of j means nothing but the vector containing this. Don't be confused. Gradient means this, the partial derivative stacked one over the other. So what is the partial derivative of j with respect to theta 1?
1 upon 2m into 2
Yes.
Summation over theta 0 plus theta 1 x minus y whole square
Whole
into
square will go away,
x.
right? So this is
Yeah.
minus. So by chain rule, this is minus 1. So taking the derivative of this function, right? So you took
Yes,
two
sir.
outside, two outside. So it's ddx of x to the power n is n into x to the power n minus 1. So 2 is going away. And into x, right? You're correct.
Yes, sir, into x.
Yeah. So this is what we will calculate now. So I equal to 1 to n. So you're told theta is equal to 2 comma 1, right? So never put the theta before and take the derivative. Then it's at most fully wrong, right? So you have a Preeti has a raised hand. You can go ahead.
She will ask her to type her question in the chat box.
Yeah, she can type her questions if she cannot unmute herself. Anyways, so this is the derivative. So let's put the values and just see. 1 by 2 into 4. I have 4 points. So what are the 4 points? Can anyone remind me if anybody has written it down? So I will not have to look back. So I'll remove this 2 and 2. I'll cancel this. So 1 over 4. Theta 0 was 2 plus x.
1.
Yeah,
Theta 1 is 1.
yeah. So from I is equal to 1 to n. So xi minus yi to xi. So sorry for that. Let's see. There were 4 points. You will all put all these 4 points. So these are 6 comma 7, 5 comma 4, 10 comma 9, and 3 comma this. So you get it, right? So I'm just trying to write 1 by 4, 2 plus 3 minus 4 into x was 3 plus 2 plus
5, sir.
5 minus, oh, first one was 6, na? 6 minus 7. 6 minus 7 into 6. 5 minus 4 into 5. Please help me out with the next terms. I'll have to look up again otherwise.
10.
2
10
plus
minus
10 minus 9.
Into 10. Right? This is the equation. And the last one is 2 plus 3
3.
minus 4 into 3. Similarly, I'll not do this calculation just to save some time. So d theta 2 will be, again, someone? Go ahead. Okay. You're taking the derivative with respect to theta 1 now, theta 0 now. So not theta 2, sorry, theta 2, theta 0. So what will be this derivative? So it will be 1 by m.
2 into
There's no, yeah, 2 into, okay, I'll go ahead. 2 into theta 0 plus,
Theta 0 नहीं होगा ना, theta 1.
we had a square, right? So square has to be, first you need to follow the chain rule. And then
0 plus theta 1 x minus y.
correct. And you have dd theta 1, dd theta 0, dd theta 0. So as Professor Sandeep was telling, this will not be there. So it will just be the sum of these terms. That's it. So let's this is easier to calculate. So it's 1 plus 1 plus 3 plus 3 plus 1. That is 6, 8, 2. Is that okay? So how will you calculate the derivative at a particular point and so on? So you can do this for any number of points. You may be told to find out the derivative at a particular point and for a given data set. So this was all about week 2 and week 6. So we have referred to the end of the note. So now this is the thing that people were asking for. So let's do one important question. So first of all, I've also covered these Bayes rule in detail in week 4.
Yes.
Yeah, go ahead.
Probability of A by B is equal to probability of B by A into probability of B divided by probability of B.
One easy way to remember is whatever is by, it will be just multiplication. See, B by A into A is equal to A by B into B, right? Sort of not exactly sort of a thing, because if you do this, so this is A comma B, right? So if you write this, both of these are A comma B, right? So you have defined A given B is probability, the joint distribution of AB by probability of B, right?
Yes, sir.
So this is the way to remember. So you want to sort of multiply the term you're present in the denominator, sort of. This is the idea. So let's do this Bayes network. Consider this Bayes network. So you're told to find FC and P of FC. So we have done a more complicated question in week 4. We have done MLE, this thing, maximum likelihood estimation, maps, a priori estimation, and Bayes networks in details. So we have done very complicated questions there as well. So you can go and look for details things, but more or less what will be the structure of the questions will be something like this. It will be centered around Bayes rule or the Bayes theorem. So how do I use this? So everything, so to find C, any ideas, what do I do? So I covered this once. So you don't have that probability of C given to you here, right? So how do you find this? This is your week 4.
By the Bayes rule.
We use P of C by F.
Yeah, you'll use these two. So the idea is you use law of total probability, right? So you take the joint distribution of C and F, and you take the sum over all the even space of F, sort of. So I'll not write it this way. So Fi I'll write over all Fis, such that Fis are, I told, they are exhaustive and exclusive events. Remember, right? So they have to be exclusive and exhaustive to take this intersection to be C, right? This is your PC intersection F1. Say this is your F1, this is your F2, this is your F3, this is your F4, this is your F5. So P of C intersection F2 and so on. If you take P of C intersection P5, this is nothing but PC, right? You can clearly see that. If you can't see, you ask, otherwise I'll just go to the map. This is your C. So C intersection.
Got it, sir.
Yeah, great. So instead of doing this, what you do is you have this, you marginalize sort of over all F. So, but you're not given this joint distribution. So what do? You use Bayes rule, as one of you were suggesting. I think Soumya. So what do? You use Bayes rule as follows. So you have only two events given to you, F and F complement. So these are exhaustive exclusive events, right? F union F complement is the entire set, and F intersection F complement is empty set, isn't it?
Yes, sir.
So this actually can be used as a exclusive and exhaustive event. So F into probability of F plus probability of C given F bar into probability of F. Is that okay? And this is nothing but probability C comma F plus probability of C comma F bar. I'm written in form of a Bayes rule. This is nothing but, this is given to you 0.8. This is also given to you, what is it, 0.1, and the next term someone will have to prompt.
0.3.
3.
Into
0.9.
0.9.
correct. That's great. So this is your 0.008 plus 0.27
And 0.1.
correct. So and the last thing that you want to do is you want to find F given C. How can you do that? So I have a lack of space here, so I'll do it here. Probability of F given C. So how do we do that? Any idea?
Probability
P of C by F into P of F divided by P of C.
Great. So everybody is ready. At least some who are replying. So C given F is given to you
0.8.
0.8 into
P of F is given to you 0.1.
0.1.
0.1.
Probability of C you have calculated just now. That's all. So this was more or less with what you do in Bayes networks. So that is week 4, the complicated part. The other parts of week 4 is simple. We had done maximum likelihood estimation where you estimate the parameters using, you set the parameters according to some distribution. We had done a uniform distribution case and found it. So that class was also very interactive. You can go and watch that in the YouTube channel. That will be helpful. So this is your week 5, I think. So we have more or less, I'll cover week 1 to 6 today, because 7 and 8 we have just done a couple of days back, and we've also solved questions that were very similar to the questions that are there in the assignments and all, because 1 to 5 were the only things that we had done a lot in advance. So we are doing some easy questions today. So I would like you to recall what is an SVM. Do you all recall an SVM?
Support vector machine.
Yeah, name I know you all recall. So
Supervised.
why were these?
And we have
Yeah, go ahead.
we have the margin and
Correct. So we had done this extensive derivation with NSVMs, and we had seen people were a little bit confused also. I hope that confusion is over now. Using all this, so we computed the dual space and all. But anyways, so SVMs, the idea, so I'll just draw the idea now for you people to just sort of remember. So you'll not be given complicated questions from SVM as far as I see in the way the assignments and the videos have been structured. Anyways, since we have done it in great details, so I'll just cover the basics of it. So I'm drawing a hard SVM over here. So these are known as support vectors, right? So what do you want? What did you want? We wanted to maximize this margin, right? The idea was, and I had also drawn parallels with regularization in a linear regression, sort of a thing. So regularization in linear regression, we had done we do a similar thing, because if you have such points given to you, I had given you the intuition, which line do I select? Do I select this line, or do I select this line, or do I select this line? So I select a line that is the most robust. So it's also known as the large margin classifiers. So where this margin is maximized. So this is this is all about SVM. All the other thing is class 11 maths. Nothing else is there. So we had found out the cost function was 1 by 2 square, subject to the constraints yi y transpose x plus b I is greater than or equal to 1 for all xi. So we use the Lagrangian and all. So how do we get this? Just to recall, so we have this vector and we have this w vector. So what did we do? So x plus minus x minus, and used to take the dot product with this. This is the margin distance, right?
Yes, sir.
So this is what we maximize. So you can clearly, so as people are a little bit interested today, so I'll just do it. So wx plus b is equal to 1, right? So we had said wx plus b will be greater than or equal to 1, and wx minus plus b will be less than or equal to minus 1. Remember? To make
Yes,
this,
sir.
yeah, to make this large margin. And for support vectors, these equality hold for support vectors. Supports. So here if you just plug in this value, so x plus, so w hat can be written as w by, if you normalize w, that is x plus minus x minus. So this is nothing but the dot product of minus dot product of x minus. That's what is that from here? Do you remember? See, just subtract these two equations, w plus x, wx plus minus wx minus, sorry for my illegible handwriting and you have beard with it, so that is equal to, if you just sum this is greater than or equal to 2, or actually equal to 2, right? Because for support vectors. So this is nothing but 2 by this. So if you want to maximize this, so is in turn equivalent to minimizing this. We take the square to make the calculations easier. If you take square of a number, square is also minimized as x equal to 0. So we can always take a square of a positive number, right? So this is the norm. Norm is always positive. So this is equal to something like x square plus root over something like this. So I just take the square root of this to square of this to get this number. So this is all about SVM. So let us do a conceptual question on this. So we have also done the dual thing to solve the SVM. We had coded SVM. You can go back again and look at that. So these are all the sort of a recap. So let us see this. So let us take a 1D case. So I just figured this out, figured this question just for your understanding of SVM. So what my question is, say this is a 1D, data is in 1D, but your decision boundary is say in 2D. So what is your decision boundary? So what will be the equation of your decision boundary? Can anyone tell me? And what is the margin?
Y is equal to x is constant, no?
Here
y is constant, x is varying.
Correct. So what is the decision boundary? So x is equal to, you are correct in
x is equal to 1 to n summation of.
You want to sort of I'm asking
Y is equal to 5.5.
5.5. Oh, actually 5 na, not 5.5. 3 plus 7 by 2 is 5. I think you got it correct. It just means me did the miscalculation. So you just take the midpoint and set a line like this, right? This is what an SVM will do, and treat these as the support vectors.
Right.
So this is your margin, that is equal to 4. So all of you, please don't call me sir. So I'm just in my first year of PhD, just completed my graduate studies, undergraduate studies. So I'm in second year actually. So don't call me sir. It's a bit awkward. So what is, so margin is, so according to all of you, it's 4, and the decision boundary is x is equal to 5. So this is the SVM, just to revisit the concepts and the equations. We did this, and the last 15 minutes will be just doing week 3 or PCA. Very important question. So let us see. First I'll just intuit one thing. So let us derive one property. I have derived that later. Say x is a symmetric matrix, or A is a symmetric matrix. This is a linear algebra sort of a thing. A is a symmetric matrix, right? So what can you say about its eigenvectors? We have spoken about eigenvectors on multiple occasions here. So what does an eigenvector mean? Ax is equal to some lambda times x. So when you apply this matrix as a function, so a vector is just scaled. It's not rotated. That's an eigenvector for a particular matrix A. Eigenvector of A, such that you take the linear combination of the columns of A, you just get a scaling of x. So I don't want to go into the nitty-gritties of eigenvalue eigenvectors in this last few minutes. I just want you to realize a very important property. What happens is when a matrix is symmetric. So let us consider two eigenvectors. And this is real matrix, say we are taking a real matrix, no complex, nothing is taken. Two eigenvectors, right? Say x comma y with lambda x comma lambda y of their corresponding eigenvalues. So what are the two eigenvalue equations that you have? Ax is equal to lambda x into x, and the second one, can anyone tell me?
Ay is equal to lambda y into y.
Correct. So the idea is, let's consider this dot product, or the y transpose Ax. What can you write this as? You can write this as y transpose lambda x, right? Or lambda xx, such that lambda x is not equal to lambda y. So lambda x, y transpose x. Is this step clear? So I'm just replacing this by this equation. Correct? And thus in the second equation I'll write y transpose Ax. So we can also, this is also equivalent to Ax transpose y. So we all know u transpose v is equal to v transpose u for any. So you take dot product between these two vectors. It's also the same as taking dot products are commutative, right? Class 11 maths, physics, what to say. So you can see, so I just take the commutative property. So this turns out to be x transpose A transpose y, right? When you take a transpose of a matrix vector, so you get the inverted. This is the matrix property. So you can now change the association by the associative property, and A transpose is equal to A as symmetric matrix. So you see now, so this is equal to lambda y times y transpose x, right? And 1 and 2 are equal, right? So 1 is equal to 2, which means 1 minus 2 is equal to 0, which means lambda x minus lambda y, y transpose x is 0. So this is not equal to 0. So this is equal to 0. When are two vectors dot product equal to 0?
They are perpendicular.
Correct. So y and x have 0 dot product when they are perpendicular. So why did I do this? What is the need? So the need is to say, since covariance matrix is symmetric, just recall covariance matrix is symmetric, so all its eigenvalues are perpendicular. So you recall, so how did we define a principal component? We defined, if this is the data, the first principal component would be the direction in which the variance is maximum, right? Along the direction that explains the maximum of the variance. And then this is the u1 component, and this is the u2 component. These are known as the principal components, the direction along the vectors along this. So you try and solve this equation where you solve this. So you can go and see the videos, but this is not the thing. So we're not going to go into details here, but we'll just give you the review to remember. So when you have a data distribution, you want to keep these coordinates, right, to get the maximum spread. If you keep these coordinates, so everything will shrink, the information will reduce, right? I think now people are falling off. So this will have the maximum spread compared to if you project along this, right? So it is easy to classify intuitively on a larger spread data set. You want to keep the variance intact. So the two things that we learned is on the project along the direction of maximum variance. Number two, eigenvectors of are perpendicular. So let's do a simple exercise. Say we have two eigenvectors. You are told to project, say these are two eigenvectors for a covariance matrix that you have. So this is a very relevant question. So you will be told to find out the component along each of these eigenvectors, or write your V in terms of these eigenvectors when you do the principal component analysis. So first question of mine is W1 and W2 a proper candidate for eigenvectors? Two distinct eigenvectors of the matrix. Are they proper candidates? So U also has to have a unit norm, or they must be orthonormal, all of these vectors. So U1, so I'll go down and solve this. So U1 is equal to half, 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 and U2 is equal to 1 by root 2, 0. Is it 0? 1 by root minus 1 by root 2, 1 by root. Yeah. 1 by root 2, 0, 0. So first of all, what is the first condition you need to check? To check if they are eigenvectors, whether they are unit norm, right?
Yes.
So what is the norm of L2 norm of U1? Square root of half square plus half square plus half square plus half square, right? That is equal to, what is this value?
One by 16.
1 by 4 into 4. Each of these are 1 by 4,
Plus
right?
1.
Yeah. And this one, half plus half. That is also 1. So they are orthogonal. They are not orthogonal. They are unit vectors. So condition 1 is true. And the second condition is, if both of them have to be eigenvectors for the covariance matrix, what has to be the property between them? Just now. Yeah, go ahead. The dot product should be
0.
So is it 0?
No.
It's not 0. What is the dot product? 1 by 2 into minus 1 by root 2 plus 1 by 2, you take this, product with this, or the inner product, plus half into 0 plus half into 0. Aren't they perpendicular? So you have 1 by 2 root 2 minus, or rather minus, plus 1 by 2 root 2. Correct? They are perpendicular, right? They are orthogonal. But they are not only orthogonal, they are orthonormal. Means their unit vector is also 1. They are also unit vectors. Now any doubt regarding the dot product?
No doubts.
Okay. So there's these two are orthonormal vectors. So now, since these two are eigenvectors, you're told, see, initially you have a 4 component vector, so you want to do some dimensionality reduction into 2 components. So what is the component of U Do I have a space here? Do I have space? Yeah, I have. So what is the component of V along U1? Someone prompt. It's 1 by 2, 1 by 2, 1 by 2, 1 by 2. So you take a dot product, right? You take a when you take a component along a unit vector, you just take a dot product with it. X vector with U. That's all. So half. What was V?
Minus half root 2, 1 by root 2.
1301 V. So V you want to project, right, on this space. This is V, and these are the principal components or the vectors along which you want to project your data to. Is that okay?
Okay.
Yeah. So this is the thing. So you are projecting V onto project V on U1. So what is this value? Now I'll not do. Let me just see you people understood or not. 1 by root 2, 1 by root 2, 0, 0. What are these two components? Go ahead, fast.
5 by 2 and
Yeah, go ahead. First one is
5 by 2.
5 by 2.
First one is 5 by 2. Let me see. 3 by 2, 4 by 2, 5 by 2. Good. And the second one is
minus 2 by root 2.
2 by root 2, right? This is negative, this term.
Yes.
2 by root 2 or 1 by root 2.
Sir, I think second term is negative. It is 1 by root 2 and then minus 1 by root 2.
Yeah, so oh, really? No.
I think.
First term
Achha, okay, sir. My bad. Sorry, sir.
Okay, no problem. It doesn't matter. It's just the same thing, just calculation. So it's root 2. So how can you write? So in the new data format, what will be your data? Root 2 now. V compressed or V PCA. Is that okay? Salam U1, Salam U2. Go ahead.
It's supposed to be 2 by root 2, right?
2 by root 2 is root 2, right?
Okay, yeah.
So you have you take some unit. So you take projections along the unit vectors, and so you from 4-dimensional R4 you have reduced it to R2. So the idea is when you have an image, say we did this MNIST data set. It's a very interesting question that we had solved. I have the code available. You can go ahead and play with it. So we did this on this. Okay. So MNIST are handwritten images. So it's a 28 cross 28 handwritten images. So it's a 726, right? Or 784. Oh, how can it be 6? My bad. So 28, 864. And this is 764, I guess.
784, sir.
84, okay. Okay. 20 into 8 is 752, 648. Yeah, correct. So this is your data. So we had applied PCA on this, and we had reduced it to a data set dimension. It is belonging to 784 dimension data set, and we reduced it to just R, I think as far as I recall was around R10. This was explaining around 90% of the variance, and R70 explained 98% of the variance. You can go ahead and see these the exact details, but the thing is you could compress the data into this dimension, and when you did the predictions and all, the accuracies were very similar. So why do you want to do these things? So, and PCA is also, this can be asked, also used as a visualization tool. So 784 you cannot visualize. If you do a PCA, so you will see these are zeros, these are ones, these are 2, and so on. Is that okay? So you can visualize into 2D or 3D, and that is also a helpful thing.
784 vectors, na?
Go ahead.
784 vectors होंगे ना?
780 for numbers. It's a 28 cross 28 array. So the vector, each vector, so we had rasterized it into a single vector and used a multi-layer perceptron. If you remember.
Deeper with the data items then.
Yeah.
Entries.
So each of them were taken as a feature, different feature. And we could, each of this feature, we could reduce to a 10 hybrid dimension features. So one of the students had asked if which are these features. So my answer was that you cannot retrieve which exact initial representation of the feature was, because each of these eigenvectors are some linear combination of the initial features. So this is all about PCA. So week 1 to 6, I have sort of tried to cover. 7 and 8, we have done all the questions that are possible in the last 2 sessions that we had. So if anyone has any questions regarding today's session or the entirety of the course, you can go ahead, or we'll end this series of tutorial now.
Could you tell us in short what is feature engineering and how it is applied here?
What is
Feature engineering?
Feature engineering? I'm doing feature engineering here exactly, right? So I'm actually reducing the number of features. I'm just doing handpicking the features, but here we are agnostic to what you're doing features. So we had done feature selection in the forward pass and backward pass. So these are also feature engineering for speech, for example. So if you're working with speech, you do sometimes what you do is calculate MFCC features. That is also a feature, hand engineered feature. So also there are papers that would do take your brain data, convert them into graphs and so on. So instead of taking raw numbers, you convert it into an easier representation. That's all about feature engineering. Is basically each xi or the data point would belong to some n-dimensional space. So you have the data. I had spoken about it. So you have data, you do pre-process and extract some features. Say for example in speech. Hello, is it on your side? Yeah.
Yes, am I audible to you?
Yeah, now you're audible. Go ahead.
Dimensionality reduction and PCA are synonymous terms, no?
Dimension? No, they are not. PCA is just one example of dimensionality reduction. You can do T-SNE, you can do LDA that ma'am has covered, or the other TAs have covered. So the LDA, what it do is it takes the labels into account to make the perfect discrimination or the reduction in features. This is the unsupervised setting.
Could you list out all the options available under dimensionality reduction?
Okay, so the few I know, see there are PCA is 1, 2 is your LDA. This was covered in the course. You can just go and look at it in course.
Analysis, no?
Yeah. Then you can go and see about things like PCA, LDA. What was the other thing that I just told you just now? T-SNE, T stochastic neighbor approximation thing, embeddings. This you can do. These are traditional methods. But nowadays, what do people do? They will take this image, right? They will pass it through a neural network and they will get a feature map. So this is also an embedding or a feature. This can be used as a feature selector.
This is of CNN type, no? If it is
anything. It can be ImageNet, ResNet, an RNN, ANN, graph neural networks, anything.
And it is used for time series, no?
It can be used for time series, it can be used for images, it can be used for MRI, it can be used for videos, everything. RNNs are used for time series. Yeah, we had covered sort of CNNs and touched upon RNNs in week 6, but those are not a part of your syllabus. You don't only have MLP. So you see, so this large data can be compressed into a small data for when you're training a particular model. Say you are training a model to classify say on the ImageNet. So what does the AlexNet do? Say you have ImageNet data. So cat, dog, and so on, humans, and you pass it through a AlexNet, and you get some representation. So this representation is also this AlexNet is also a feature extractor. You can see. So, and then you use this to a fully connected layer to predict. Vectorize it to a fully connected layer to predict your task specific sort of a thing. So you can, when you are having a new data, what people generally do, they pass it through an AlexNet, get the features and do stuff like that. Is that okay?
Yes, okay.
So these neural networks can also be used as dimensionality reduction, feature extraction, etc. You can also hand engineer them if you know the field very well. If you know signal processing, you can probably hand engineer features for your particular case, for a particular application. But the trend today is end-to-end neural networks. So you are actually modeling ignorance there. So you don't use any feature extraction, give the entire data, let the neural network learn. That's the idea. Okay.
Thank you, Maina. Thank you so much for your wonderful
welcome.
session today.
Well, you're welcome. If you don't have any more doubts, as I see no more questions present. So Rishparna's doubts also I have covered. So everything has been covered. So I hope you enjoyed this series of tutorials. It was hope it was helpful, and also both in the theory and the programming aspects. You can go ahead and relook the videos and go ahead and see the codes that I have shared with you all. So I hope it was a good learning experience. Thank you, everybody.
Thank you so much.
Thank you so much.
And all the best for your exam.
Thank you, sir. Thank you.
Give
Thank
the
you, sir.
exam. Yeah, good. All the best. Bye.
Bye.